Welcome back, my statics friends. In previous videos, we talked about a methodology known as equivalence, where we were able to take a system with forces and moments and convert it into a new system with different forces and moments, or total forces and total moments, through single force resultants or equivalent force couples. In today's video, I'm going to show you how to apply this to scalar values such as area or mass or gravity to find where the center of mass is or the center of area is. Using a similar technique, I'll walk you through the basic equations and then we'll work an example problem. So without further ado, let's get started. In statics, centroids are a very important calculation for figuring out properties of an object. Ask any engineer who's ever done any sort of design or analysis work, and they have done a whole lot of these type of calculations, finding out where the center of a force is being applied at, or where the center of mass of an object is, or calculations like that. They're very important and very necessary for calculating other things, such as other section properties, such as the moment of inertia or the second moment of area or any number of things. This is the starting step for those particular calculations. Now, there are a lot of different types of centroids, and in a lot of engineering problems, we often assume that these centroids occur at the same location. So a centroid is basically a coordinate value for a kind of a total resultant acting on it. And so common ones that we'll see are the center of area, the center of mass, and the center of gravity. And we can kind of relate this to our equivalence technique that we talked about in one of the earlier videos. So what I've done is I've kind of drawn up a crude diagram of a before system and an after system. And we're going to be looking at the areas and how we would come up with the particular values. All right. And so what we look at and what we have happening is that I have this, general arbitrary area that I've divided into smaller pieces. And what I've done is I've shaded one of these pieces and I call that as my AI element. Okay, and so we know that this guy is located in space such that this distance is xi, and maybe this distance would be yi, and that would give me the coordinates of where this element is in space. And the smaller the piece that you work with and the more pieces you break this thing up to, the more accurate of an estimate we can get for this equivalent that we're trying to do. So if we look at that, so there would be a whole lot of these pieces that all have a different a associated with. So where I then is going to be, I is equal to 1, 1 to n, if you will, as we start to kind of look at that. That doesn't look clear, but we'll clean that up a little bit. Okay. So I broke my pencil in. We're off to a flying start here, aren't we? I equals 1 to n, where n is the number of elements that we broke this thing up into. Okay, so that's kind of my before situation. And what we can do is we can say, well, instead of dealing with all these individual areas or all these individual masses or all these individual gravities, often we want to be able to handle them in a very succinct, collective way. And the way that we do this is we could draw an after picture in which I take all of the area that is here and I lump it together into one total area that I'm going to call as a total. Now, I drew it as an arrow. It's not a vector. These are scalar quantities. Technically, gravity is a vector, but we would be assuming that all of the directions are consistent within the realm that we're looking at. But that's a discussion for another day. But so we're going to take all of this area and I'm going to apply it at a single point. And that point is going to be located at a distance that we call the centroid distance, which is in the x direction we call it as x bar, and in the y direction we call it as y bar. Now again, this is all being measured relative to a reference, and the reference has to be the same on both the before and the after. So what we can do is we can kind of apply kind of some of our equivalence relationships that we did before. If you remember, in equivalence we did two different steps. We did a resultant force step, and then we did kind of a moment step. So if I take a look in the first one and let's just do the resultant total. That's kind of what we did with the forces, right? It was a resultant total force. Well, now I'm going to do a resultant total area. So in the before picture, all I do is I do the sum of I equals 1 to n of all of those AI values, and that would be the before. Okay, and then after, we've converted that to an A total. Okay, so my equation is sum of the forces I equals 1 to n of AI is equal to A total. Okay, and so that's like our force resultant equation. Okay, the second one we did was always a moment, which was I take the value multiplied by a distance, and we could use this to in turn figure out where the combined resultant is. This is like the single force resultant calculations that we did back when we were doing equivalence of forces. Okay, and so all I do then is, so for, let's just look at the x direction only. I'm going to sum all of these I values. So I again equals 1 to n again of basically xi, which is what I said was the coordinate of the piece that I'm looking at, okay, multiplied by the area of the piece that I'm looking at. So that would be my calculation. Now again, we're doing distance times area of each element that we've broken this piece up into. And then the after effect of this would be, it's going to be my x bar centroid distance multiplied by my A total would be the after that happens. Now again, you could do this in the y direction, you can do this in the z direction. It all works out exactly the same way. Okay, and so this, if you look, is kind of a distance times an area. Well, if I change the A to an F, this is a distance times a force. This is the moment equation or the moment equivalence that's happening on this. Okay, so this is a way of kind of taking kind of an average and doing, it's really a weighted average of collecting all these points and turning them into a singular value at a singular point. Okay, and so when we do that, okay, if I take a look at what I would call as equation 2, that's this one. Okay, I get the sum of the xi ai for I equals 1 to n has to then be equal to x bar times the A total. And again, we don't know x bar. We know A total from the first equation because presumably I have to know all of the values of the AI values. Okay, and then presumably you know where all of those values are located so you can multiply those together. So I get sum of I equals 1 to n, xi ai is equal to x bar A total. And so if I rearrange this a little bit, I can actually calculate x bar, which is, again, x bar is the position that locates the total area resultant in the x direction. Okay, and when I do that, you get an equation that looks like this. It's the sum of the xi ai all over A total. Okay, and I can rewrite this into the classic form that we know, that is the sum of the xi ai all over the sum of the ai. You'll see this formula repeatedly scattered throughout texts. Okay, so this is the x bar formula. And if I do the same thing in the y direction and the z direction, you can find the centroids in those directions as well, where now I take the y coordinate times its area over the sum of the ai and the z coordinate times the area over the sum of the ai. So these are very common calculations that we do in engineering, because what happens is this center of area calculation that we've done is actually, it's the centroid, and it's where axial forces in an object work. It's where, you know, it's kind of a balance point can occur as we start to kind of look at things. And we'll show you a whole bunch of examples where these work off of. A lot of the section properties that you'll do in your dynamics classes and in your mechanics materials class, and a lot of the later classes that you do in your major will all start with this step. So we always do these diagrams. In fact, it's so important that in a lot of my classes, you know, one of the earliest things I have them do is I have them generate a calculator that does this for them for a group of areas, and I'll show you an example of how we start to kind of work this thing out. Okay, so that's our basics, you know, using kind of a discrete summation approach. Now there is an integral approach that we'll talk about in the next video where I can do it for, you know, integral areas, but I'll show you the power of what this method can do with a simple example, and we'll do that right now. Okay, all right, so here we go. If we look at this, okay, I've got an example. What we want to find is the centroid areas. I would say we can add or subtract areas, but I can look at, you know, breaking this object up into pieces. And so say, you know, I have this kind of triangle element that is 3 foot wide, it is 3 foot tall, and then I have, you know, a rectangle that is 2 foot times 3 foot tall is this portion, and I have this little guy here. Okay, and what we can do is we start to kind of look at these values is we can kind of break this up into a bunch of areas, and there's a lot of different ways that you can do this. One methodology might be to just break it into these areas, in which I do a 3 foot triangle, a 2 foot wide rectangle, a 1 foot wide rectangle, and then these areas. This area would be the same as what I've done here. Okay, and each one of these areas would have a centroid for its particular area. And you know what the areas of all these regions are. You can find the area of a triangle, and you can find the area of this rectangle and the area of this rectangle. So we can start to kind of apply our methodology, or we could do it another way in which I overestimate and do a 3 by 3 rectangle, which means I've now overestimated this little corner piece. Triangle is still the same, and then I can subtract off a negative area of this little guy, and I will get the exact same answer. Okay, as we start to kind of look at this. So what we'll do is we'll go through, and in this particular example, we're going to do the subtraction approach. But again, you can do it any way, and you'll get the exact same answer. So all we're going to do is we're going to make a table to basically be able to find all of my calculations that were needed for this formula. So I'm going to need an XI location, an AI location, and then I'm going to have to do some summations, and then I'll have a product of XI times AI. Okay, so let's go through and let's look at this. So what we're going to do is we're going to call, in our particular case, we're going to say that region 1 is going to be my triangle. All right, so this is region 1. Okay, and this is going to be region 2. And then this little guy over here is going to be my region 3. Okay, and so if we start to kind of look at that and start to apply these rules, all we're going to do is we're going to make a table. The first line, column in the table is we're going to compute the area of the region that I'm looking at. Okay, so for the triangle, it's 1/2 times 3 times 3, or 4.5 feet squared. Okay, the centroid of this, now this depends on these xi, yi dimensions are measured relative to a reference. Okay, so in our example, and you can choose the reference to be anywhere that you want. You know, again, in my class and problems, generally you're given that, or you will assume that it's the lower left or something. But for this, they're assuming that the reference is here. You can see you've got your x-axis and your y-axis, and this is the origin. This is the reference point. All right. Is that. And so what we're looking at is relative to the reference, which happens to be at the interface of the triangle and the rectangle. It's this vertical line here. Okay, where is the centroid of this triangle located? And the answer is, well, we know that the centroid of a triangle, if you remember, triangles are, in fact, we'll write this down, that if I have a triangular shape here, okay, the x bar distance from the high end, x bar is 1/3 of the base dimension, where the base dimension is going to be this guy. Okay, if I call the height as this one, then y bar is 1/3 of the height. Okay, now the triangle has to be oriented exactly like that. If I come and I do it from here on this shape, okay, the centroid is now here. Here's the 1/3. Right, it's 1/3 from the high end, and likewise from here, that would be 1/3 of the height. Okay, but then you notice that my reference point is down here. You would have to subtract b minus the 1/3. So what happens is this dimension becomes 2/3 of b, and this dimension, again coming over to this one, becomes 2/3 of h. So when we say it's 1/3, it's 1/3 from the high end. Okay, and then sometimes you have to do this correction that happens there. Likewise, if we look at a rectangle, okay, well, it should be fairly obvious. Where's the centroid of a rectangle? It's in the middle. So if this is a b from here to here, and this is an h from here to here, then this is b over 2, and this is h over 2. And again, we've assumed that my coordinate system is that lower left corner, if this is my O. Okay, now in a lot of textbooks, they will have charts that have a lot of these values set up for you, and I'll show you those, but these will get you a big portion of the way through things. Circle is exactly the same. Okay, but often my circle, we look at setting the reference in the middle. So here, x bar is 0, y bar is 0 for a circular value. But if you wanted to choose to set your reference down here, well, then all you have to do is figure out where in space that guy is, and that becomes, you know, an x, and then maybe this becomes the y, and you can locate the center of the circle, and that becomes your reference from that new reference, how far it is to the center. Okay, so these are the areas that we're dealing with. I'll shade these a little bit so you can be clear on which areas it is that I'm talking about. Okay, so that's all there is. Those three will get you a long, long way in our particular calculations. In fact, that's what we need to be able to do this one. All right, so we've got our area for our triangle. Again, we're looking at region 1, our triangle. And so if the base of this thing is 3 feet, then the x distance from this corner to the center of the triangle is 1/3 of 3, or 1 foot. So we'll just write this out. 1/3 of 3 equals 1. And then this is 1/3 of 3 equals 1 is how I got those values. Okay? So it's 1/3 horizontally in the x direction. It's positive because we're going towards the positive x. So again, you got to put signs on this. If we go to the left, it's going to be a negative value, and that's what kind of balances things out. Okay, and then y positive is now our upward direction. Okay, and so that was the 1/3 of 3 for that one. Okay, and then all I have to do for the rest of this line is I take xi times ai. So I take my xi value and my ai value and I multiply them together. I get 4.5, and that's units or feet cubed. And then my yi ai value is also yi times ai, 4.5 feet cubed. Very simple, very straightforward. Okay, now the big area that we have, we know, is 3 foot by 3 foot. Okay, it's 3 foot on the bottom, 3 foot high. So that's going to be 3 times 3 is 9. Okay, and then the center of this, relative to my origin at the exact same point, is now minus 1.5. Okay, it's half of the base. The base was 3, so minus 1.5 is that value. And then to get to the centroid in the y direction, I have to go up a positive 1.5. Okay, so then I do my xi ai calculation. So minus 1.5 times 9 is minus 13.5. And yiai is 1.5 times 9 is positive 13.5. Again, you got to watch the signs. Keep those on there. Okay. Then the next little piece that I do has to do with this little chunk that we're subtracting, that extra little corner that it was missing in the upper diagram. Sorry, pull this down a little bit. The piece that was missing up here, this little piece. Okay, so I've subtracted that chunk out of the big circle to get the total area that looks like what I'm after. Okay, and so my area of this is 1 by 1. Or sorry, 2 by 1, 2 foot high, 1 foot wide. It's a rectangle. Okay, and because it is being subtracted, I put a negative sign on it. Okay, and so then the centroid, where's the center of this guy located? Well, if you look, again, we're measuring relative to this point. So to get to the center of that rectangle, you know, I go over 2 feet and then I go over half of 1. So my total distance negative is minus 2.5. Right, and so that's my minus 2.5. So it went in as a minus 2.5 here. Okay, to get to this guy, to get up to the center, I'm now going to go up 1 and then plus a half of 2 gets me a total of 2 feet up. Okay, and that's where the positive 2 is coming in here again because we're going in the positive y direction. Okay, so far so good? Good. All right, so if I go through, I can now do my multiplication. xiai is minus 2.5 times 2 is positive 5, and yiai is going to be equal to positive 2 times minus 2 or minus 4. Okay, so that's how you do the tabular values. And for every area that you break this into, you would write another row and another set of pairs of values of x, y, and then these product calculations. So really the only thing you're really calculating or having to figure out from a static standpoint is where's the centroid of the areas and what's the total area for the center of area calculation. So we're going to do sum of ai is going to be equal to, if I take these 3 values and add them together, well, that's the sum of this. And you know I need that for my formula, so 11.5 feet squared. Okay, and then I can go through and I can sum my xiai column. If I add up 4.5 and minus 13.5 and 5, I get a minus 4. Okay, and the units on this are feet cubed and feet cubed on this. And then likewise, the sum of the yiai is 4.5, 13.5, and minus 4 gets me positive 14 on this. Okay, so then we can find the equivalent center of area of this. Okay, and that would be x bar is equal to the sum of xiai all over the sum of ai. So I'm going to take my minus 4 in the top. That was the top term. That's why we did the summation. And I'm going to divide it by the sum of ai, which was my 11.5. And so if I do that, that's minus 4 feet cubed over 11.5 feet squared. And that value is going to be minus 0.348 feet. So the total area, the centroid of that is located to the left of the origin, that amount, minus 0.348 feet. And likewise, I can do y bar then on this as doing the sum of yiai. So now I'm taking this value, 14, and I'm dividing by sum of ai. Notice the bottom never changes. And that's 14 feet cubed all over 11.5 feet squared, or a distance of 1.22. So the total of this, basically the centroid location, you know, you would write your answer as the centroid is at these coordinates. And again, this is x bar and this is y bar. That's what we're finding. And these are the values that go with it. And so that is a very special point in the world of engineering. And you've just done your first calculation for the center of area. Okay, so it's pretty straightforward on this. Okay, in the next video we'll show you how to do integration, but we'll talk a little bit more about some other types of centroids that you might see. Okay, the center of gravity, or the centroid, is the location at which the weights, so center of gravity would be kind of where's the gravitational our gravitational value located. So suppose I have a bunch of particles in space. These could be planets. Maybe I have, a gravity or a weight of a particular mass object. Okay, we could also be kind of doing some summation or centers of masses on this. But I turn this equivalent into what would be, so my before would be all of the little circles, and I turn that into an equivalent weight total acting here. Okay, that is now located at some point in space that is x bar, y bar, and z bar, based off of every one of these having their own xi, yi, zi values. Okay, and so it's just like what we did before, and this value is used frequently in mechanics and dynamics and even in structural analysis. But it's that whole idea of doing a single equivalent resultant. You heard those terms before. That's what we did with the forces. Single force equivalent resultant. It's the same idea. And so when I do this, the same derivation can go through, and you can see that, well, the centroid location then is the sum of xi wi all over the sum of wi. So this is basically the center of weight. Okay, we could do it for masses. We could do it for gravity values. If each one of these objects had a different gravity value, I could figure out what it's doing. And if you look at what we're doing, this is kind of like taking a weighted average, if you will. I'm taking a multiplier times an independent value and dividing it by the total. So this is kind of a weighted average that's happening here. And likewise, I can do the same thing for y bar and z bar. And we'll show you a bunch of others that can happen. Okay, some of the others that you might see are that the x bar m, which would be for the mass, would be the sum of xi mi all over the sum of the mi. So that would be center of mass. We could do x bar for g could be the sum of xi gi all over the sum of gi. So all of that will start to work. And that, oops, my line didn't come in. Looks something kind of like this. So it's the same form of the equation for the centroid. It's just what are you trying to find the centroid of? And all of these are scalar values. I mean, this could be technically this could be a vector. These could be the gravitational acceleration factors on planet Earth. We know on the planet it's not constant. That it's different values at the equator than it is at the poles, that it is up high in the mountains, that it is closer to the core of the Earth. Okay, and so you could go and figure out where the mathematical center of gravity of the planet Earth is if you had enough geospatial data to be able to define all of these values. Okay, but that's kind of where we're going with all of this. So I've given you kind of just a first look into centroids and some of the more popular ones. Finding the center of area is by far the most common in mechanical and civil engineering, but you'll do others, especially in physics. You'll get into center of mass and center of gravity and a bunch of other stuff. For a lot of what we do, though, as civil and mechanical engineers, we tend to stick mostly with centers of area. And so that's what we're going to do. So I hope that's made sense to you. It's a fairly short lesson, I know. Again, there are lots of different ways to work an object out. In our example, again, we had two ways. If you did this one without subtraction and we did this one with subtraction, you will get the same number if you do it correctly. So however you break this up, it's not, not uncommon. So, if I have, say I had a hole in this object, a round hole, well, I could subtract off the whole area in its location, and we can start to kind of work some of those values. So I hope that's kind of made sense to you. If you got any questions, as always, leave us some feedback down below, and we'll be happy to help answer your questions. Otherwise, toss us a like on the video, and be sure to subscribe to the channel, and we will see you guys next time. Happy engineering.